An electron and a neutral carbon atom are initially 1 times 10 to the negative 6 meters apart, and there are no other things in the vicinity. The polarizability of a carbon atom has been recorded to be 1.96 times 10 to the negative 40th coulombs times meter over newtons per coulomb. Alright, so calculate the magnitude and direction of the acceleration of the electron. Alright, so what have we got here? We've got a neutral carbon, we've got an electron. So this neutral carbon is actually made up of a bunch of different charges, and they're going to react when this negative charge comes along. So, first things first, the electric dipole moment of an induced dipole is P equals Qs, where Q is the charge of the dipole and S is the distance between the dipole. So, it will be this charge and this charge separated by this distance. Alright, and the polarizability alpha is just a ratio between the dipole moment P and the electric field, which is what we're about to solve for. So, right here, alpha equals PE, or P over E. So then we plug in QS for P, giving us the value that we're going to look for. So, just plugging in things. This is the charge of a proton, this is the distance, and this is our polarizability, giving us 8.16 times 10 to the 14th newtons per coulomb. So, using Newton's second law, we can use the electric field in relationship with the electric force law to solve for the amount of force that's going to be put on this electron. But based on the amount of force, we can actually solve for the acceleration. So, F equals E1Q. Alright, and then mass times acceleration equals E times Q. So, just solving for A, which is what we're doing, this is what we get. So, flipping this over. So, now that we have A, we know the mass of a electron, it's real small. And then we've got the electric field and our charge, and this is what we get. So, this is how fast this electron is just going to shoot away from this, this carbon atom. But let's say, what would the acceleration be if the electron and carbon atom were twice as far apart? So what we're going to have is we're going to solve for the electric field first, the same way we did it, except we're just multiplying by 2, and that'll give us this. So A2 is going to be equal to that times, the charge, once again, over the mass, giving us 2.81 times 10 to the 26 meters per second. So comparatively, how much faster is that? Well, we have both of these accelerations, and we're solving for one or the other. So, just moving that around, we know that A2 is going to be almost 2 times slower than A1 because, it makes sense. If they're closer together, there's going to be more force on them. So, 1.96 times A1. So, I guess I could plug that in and get like an actual numerical value, but it's not that big a deal. But if you're following along in your textbook, the answer in the textbook is actually very wrong. They give you an answer that's not even an acceleration. So there you go.